Okay, so before moving on to the next subtopic, I just would like to do some sample problems regarding what we have discussed thus far. So from one of our reference texts, it says here the voltage waveform. We have here the sinusoid, and we are asked to find the peak voltage value, the angular radius, angular frequency, the frequency, the period, and then some voltage values at time equal to 1 milliseconds. So we are to evaluate this sinusoid. We associate this one right here um, to this function, and somehow we can get this uh, magnitude of the voltage. Okay, so let's start. So for that solution, so number one, first let's check our waveform. We said that we base our function in terms of cosine. So anything that's given in sine, we need to convert that to cosine. Okay, so first convert the sinusoid to cosine. And by the way, I forgot to give you the conversion. Let's say we have some sine omega t, let's say plus some angle, then let's say it can be plus or minus, depending, right? So we can have, if we want to convert this, then that's going to be cosine omega t. If this is plus, then it will be, sorry, I think we still need to write this v, or this angle. If this is plus, then this one will be negative. If this is negative, then the other one will be plus 90. So that is the relationship of the sine to the cosine, or that's how we are going to convert the sine to a cosine. Okay, so recall that. Let's label this, or let's highlight this. So now the next step is, or we should write first, so v of t in terms of cosine, that's going to be 170 cosine, so 377t. We just have to copy that, and then plus 45, because that's the given angle, plus 45 degrees. Okay, so now let's check, is the sign positive or negative? We see here it's positive. So if it's positive, then we have to subtract a 90 degrees, minus 90 degrees. Okay, so 170 cosine, 377t, 45 minus 90, that's going to be negative 45 degrees. So that's our sinusoid in terms of cosine function. Okay, so next is, now let's find the value of this peak value Vp. So from the from the given sinusoid, Vp is equal to, so recall from this expression that the value right here before the cosine, that's the peak value, right? That's the maximum value. So Vp is equal to 170. Okay, the next one, of course, in terms of volts, that's the units. We can write units of volts right here, or V, we just have to type. Next one is omega, the angular frequency. Omega is So from this expression, the omega is the constant, or the coefficient of the variable t. So that's 377. 377, the unit is in radians per second. Okay, next one is we are asked to find the frequency. Okay, next. So to find frequency, we will be using this equation. Omega is equal to 2 pi f. We have the omega, we know, or we can divide it by 2 pi to find the f. So omega is equal, or divided by 2 pi is equal to f. So if we substitute the value, we have 377 divided by 2 pi. So f is equal to, so 377 divided by 2 pi, this is equal to 60 hertz. 60 hertz. Okay, next one is we are to find the time, the period. Number 4. So calculating now t. So recall from this expression, f is equal to 1 over t, and t therefore is equal to 1 over f, and we know that f is 60. So 1 over 60, that's right. So 1 over 60, that is equal to 0.16, and that's repeating, so 167. Okay, so 0.167 seconds, or if we move this 1, 2, 3, that's gonna be maybe, and let me check it once again, 0.16. This should be 0. So 0.0167. So if we move this 3 places to the right, 1, 2, and 3, then that's gonna be 16. So t is equal to 16.7 milliseconds. Okay, next, the shift angle. The shift angle is phi is equal to this, right? 4 to 5, but negative 4 to 5. So this is negative 4 to 5 degrees. Okay, and lastly, we are asked to evaluate the function with t is equal to 1 milliseconds. Right, so evaluating now the function at t is equal to 1 milliseconds. Right, so this is milliseconds, and when using this expression, the units must be consistent. So this one should be in volts, this one should be in volts, this one should be in radians per second, right? Radians per second. This one is per second, and then this one should be in usually this is given in terms of degrees. Okay, so just some couple of notes here. Whenever we are taking cosine of something, whether omega as omega t plus this phi, everything that's inside here is actually a unit of angle. So a unit of angle. And recall that angles can be in terms of radians, or can be in terms or radians or or degrees. Commonly, these two are the units that's often encountered in our computations, radians or degrees. But this one right here, the omega is in radians per seconds, the time is in seconds, and therefore the unit will be in terms of radians, right? So radians, but this one is in terms of degrees. So we must be consistent If we want to be in radians, then we will convert these degrees into radians, or if we want to be in degrees, then we need to convert these radians. Okay, convert to degrees. Okay, so why do we need to convert this one to degrees? Because right here, if you notice this point right here, that's the um, that's that means that our computation is in terms of degrees, right? If shift mode, you click this. If you want to be in radians, then we have to select this, but the default is the degrees, so that's why we need to convert the radians or the angular frequency in terms of degrees. Okay, so to do that, then let's write it here. V of t actually evaluated at 1 milliseconds or 1 ms, and again we need to be in the base units, that should be in seconds. So this is 170 cosine of the radians per second. So what's the radians per second, or the angular frequency? That's 377. And we need to convert this radians per second in terms of degrees. So how do we do that? So recall once again that here's our circle. We start here. Let's say 0. This is 90 degrees. This is 180, and this is 270 degrees. In terms of radians, this is 0. This is pi over 2. This is pi. This is 3 pi over 2, and this is 2 pi. So therefore, we can write our conversion as maybe from here. So 1 pi radians is just equal to 180 degrees. Okay, so or you can write 180 degrees in 1 pi radians. Okay, so this one is in radians. So I write it in this form so that I just kind of flip it so that I can cancel out the units that I don't like, that I will not be needing. Okay, so 377 radians per second times 180 degrees all over pi, pi radians. So radians, it will cancel out. Okay, so that's it. This is degrees, this is radians, and we have the unit of time. What's the time? This is radians per second, by the way. So the time is 1 millisecond. So 1 millisecond is just 1 all over 1000, and that's going to be in seconds. Okay, then the next one is 45. So minus 45. So minus 45 degrees. Now let's compute this. Okay, so we start with this. What's inside? So this is 377 times 180 divided by pi. Okay, times 1 all over 1000. Okay, and that's 21.6 minus 45 degrees. Okay, negative 23, and then we take the cosine answer, that's equal to 0.91, and then times the value of 170. 170 times the answer, and we have 156. This is equal to 156.02 volts. Okay, so let me erase this. Then the next one is, let's check what if we use the cosine. So to check using sine functions. Okay, so V evaluated at 1 millisecond is equal to 170 sine of the same values here, 377 times 180 divided by pi divided by 1000. Instead of negative, we will be using positive. So let's check if we have the same value. Okay, so compute once again. We have 377 times 180 divided by pi, okay, times divide, or maybe times 1 over 1000 plus 45. Then we'll take the sign and then times 170, and what we get is 156. 156. Alright, 0.02 volts. So it's the same thing again. Now let's move on to our next subtopic, called the phasor concepts. Earlier, we expressed the waveform in terms of, we deal with the mathematics of the sinusoids, and it's maybe relatively intimidating because we deal with sines and cosines or trigonometric functions. But there is a better way, or a more convenient way, or you can say easier way than that, and that's translating or transforming the sinusoids into another domain, and that domain is what we call the phasor domain. Now let's define what is a phasor. A phasor, it says here that it is a directed line segment rotating in a counterclockwise direction at a constant angular velocity. Again, it is a directed line segment rotating in a counterclockwise direction at a constant angular velocity. So if it's a line segment, then that means that it's a line but it has a direction. So it's essentially a vector. It's actually a vector. So recall in your subjects in statics that a vector is a directed straight line whose length, if we're talking about quantifying the length, then that's going to be referring to some magnitude of that vector. And it says here is a rotating vector, or rotating in a counterclockwise direction. So it rotates counterclockwise, and the rotational speed, or the angular velocity, is constant. So right here we have a representation of a phasor. Let's say here's our origin, relative origin. Then we have this phasor right here, a directed straight line, and that phasor is rotating at some angular speed. And there is an equivalence, as I've said, that the length of this phasor refers to the magnitude or the amplitude of this waveform signal. And then the angle, this angle right here, that refers to the shift, or the phase angle, or the phase shift in terms of the waveform. And recall again that when I say phase shift, it somehow a relative displacement between the two waveform, or one waveform from a reference waveform, or a reference point. Okay, so that's the counterpart of the phasor to the waveforms. Or the amplitude is the length, and the phase shift would be the angle. I have here downloaded some GIF from the website, or from the internet, and from this reference, designed by Electric Shocks, so credits given to them. This is a rotating vector in the left side, and on the right side, that's the waveform generated. So you can see here we have a fixed point at the center, then it's rotating counterclockwise. Somehow that rotation is related to this waveform. Okay, so that line segment, directed line segment, is what we call the phasor. Okay, so next one is the phasor in terms of mathematics. It's actually a complex number. So recall that this is our sinusoid. This is the expression of a sinusoid, and commonly referred to as in terms of a time domain representations, in terms of a as a function of time. Then if we want to transform this into a phasor, then the mathematical expression would be something like this. So the V, and I've written that as another something like this, just to indicate a phasor. But sometimes I may not write these additional lines. Okay, so for now, that's the phasor. V is equal to V, the magnitude. This one is the, let's write it here. This is the magnitude, and this one is the phase angle or the phase shift. Okay, so again, it's the angle. That's the angle symbol of the angle, and the angle is the phase shift. So what will happen is that if this is our sinusoid, in a time domain representation, so this phase shift, right? So this phase shift goes to this side, and the magnitude or the amplitude goes to this side, right? So that's the transformation in terms of mathematical expressions. Okay, so now let's do a sample problem. Next sample problem from another one of our reference texts, Shom's outline electric circuits from these authors. It says here, represent the sinusoid in terms of phasors and draw the diagrams. We have two phasors. We have sinusoids, voltage, and this is the function in terms of voltage, and then the current in terms of this function. One is in cosine, one is in sine, and we are asked to represent this sinusoid, transform this in terms of phasors, and we are also asked to draw the diagrams. So the drawing of the diagrams is simply to give us a feel on how the phasor will look like in terms of this phasor diagram. Okay, so first one is for the solution. So convert, since we have a sine, then we need to convert this. So convert I in terms of cosine functions. So how do we do that? So I is just simply 3.0 sine 2000t plus 30 degrees. This one is positive, so it will be minus 90 degrees. Right, so 30 minus 90, that's gonna be 2000t, that's gonna be minus 60 degrees. Okay, so now converting now V and I to phasors. So maybe I'll just write it here. At the moment, I'll just write the phasors right here. So for the V, the phasor of the voltage is equal to, so take note again, this is the magnitude, and then this one is the angle. So that's gonna be 150 angle, okay, plus 45. And then for the I, so again, here's the magnitude and here's the angle. So magnitude is 3.0 and the angle is it should be in terms of cosine, so minus 60 degrees. So here's our phasors. Okay, so now let's draw. And number 3, draw the phasors. Okay, so to draw that, we have here the magnitude and then the angle. So 150 angle 45, and the angle is positive. And recall that anything counterclockwise is positive, and any clockwise rotation that's going to be the negative. Let's say negative 60. So from the reference point, it goes here, that's negative, and if it goes upward in a counterclockwise direction, that's positive. Okay, so 150, that's the length. Here's our phasor. Right. Okay, so plus 45. So here's 150, and the angle is 45 degrees. This will be V. Okay, next for the I, this is negative 60, and we only have 3. So it must go downward. It is 4 to 5, probably this is 60. So 3.0, that's the magnitude, and right here we have 60 degrees. So 60 degrees downward because that is negative.